Hello, my name is Ima Frank, your mathematics tutor. In this package, we are going to study trigonometry. I urge you to bring your book and your biro so that you can take down all the things I'm going to teach you. But before we start, let's look at the behavioral objectives. At the end of this teaching, the students will be able to perform singular measure. The students will be able to solve trigonometric equation. The student will be able to state the trigonometric identities. These are the objectives. Now, let us start. Like I said, the topic is trigonometry. Consider the line OP. That is this line. Consider the line OP. Now, suppose this line rotates to another point, say point OP prime. Suppose the line OP rotates to rotate about 0.02. Another point, say OP prime. Then we have the diagram. As shown, we have a diagram like this. At this point, which was P, it means that it has left this point to another point. Call this place P prime. And so this is the rotation. This is the rotation from here to here. It's moved from P to P prime. Now, when a line rotates in this nature, it sweeps out an angle. Sweeps out an angle. So let theta denote the angle. Then we'll have the diagram in this form. Now, see the diagram. This is point O, where we had the line before it now rotates. So meaning that the line has left this point and rotate from here to another point. The rotation here. Then we call this point P prime. And it forms an angle theta. Look at that. You have theta there. So it forms angle. Now, theta, the angle theta, can be measured either in degrees or radians. You can measure this angle either in degrees or in radians. Now, when angle rotates, when a line rotates in this form, the angle measured is what we call circular measure. The angle that is formed there, when we measure it, that is what we said, circular measure. So the angle theta can be measured either in degrees or in radians. Can be measured in degrees and in radians. Or let's put or in radians. When a line rotates from the starting point and back to starting point again, we said that it has rotated 360 degrees, which form a complete circle. Now look at this line. This is the position of, this is 0. This is 0, where a line starts to P. Right. If it rotates from here and back again to this point, then it has rotated 360 degrees. Okay, so, and we see that this forms a circumference of a cycle. It forms a circumference of a cycle, which is equivalent to 2 pi. We can convert degrees to radians and radians to degrees. It's very simple to do that. For instance, since we say that 360 degrees equal 2 pi, so it follows that 1 degree will be equal 2 pi over 360, and that gives us pi over 180. Now notice that. So 1 degree is equivalent to pi over 180. Now, most times angles are given in their multiples. Angles are given in their multiples, and we can also convert it to its equivalent radians. So this will take us to some examples on conversion of angles to radians. Conversions of angles to radians. Let's take these examples and see how we can convert from degrees to radians. Now the example is convert 180 degrees, 90 degrees, 45 degrees, 30 degrees, 60 degrees, 120 degrees, 270 degrees to radians. Let's take the solution. We said earlier that 360 degrees equal 2 pi. So that will implies that 360 degrees, I'm looking at solution of 1, I. So 360 divided by 2 will give you 2 pi divided by 2, because we know that 360 divided by 2 will give you 180. Then we have 180 degrees is equal pi. So 1 pi is equivalent to 180 degrees. The same will be true for 90 degrees. We can also convert it. That is, I know that 360 degrees equal 2 pi, and that for me to get 90 degrees, it must be 360 degrees divided by 4. Give me 90 degrees. So I'll have this. Divide by 4. Then I have to divide this side also by 4. So this gives me 90 degrees equal pi over 2. If I don't want to use 360 to get 90, I can also start from here, 180 degrees, divided by 2. I will have 90. Then I will have pi over 2, which is the same thing. So if I also look for 45 degrees, I can start here. I know that 90 divided by 2 will give me 45. So that means I will have 90 degrees divided by 2 equal pi over 2 over 2. And that gives me 45 degrees equal pi over 4. So it means that 45 degrees is equivalent to pi over 4. I told us that angles are given in multiples. So now 30 degrees. How do we get 30 degrees? I know that from 180 degrees, if I divide it by 180 divided by, yes, 180, yes, divide by 6, 180 divided by 6 can give me 30. So what I will do is, and I'll say 180 degrees divided by 6 equal pi divided by 6. Now 180 divided by 6 give me 30 degrees. That shows that 30 degrees is pi over 6. So this is how we convert. Another one is 120 degrees. 120 degrees. I know that from 360 degrees, to get 120, I have to divide by 3. So 360 degrees equal 2 pi. Divide it by 3, that is both sides by 3. I'll have this. That means if I divide here by 3, I have 120 degrees equal 2 pi over 3. We look at 270 degrees. And we know that 270 degrees, let's use this in this way. 270 degrees equal 3 times 90 degrees. Yes, 3 times 90 degrees. And that will give us 3 times 180 degrees over 2. Of course, 180 degrees over 2 is 90 degrees. So we can represent 90 degrees by 180 degrees over 2. And that will give us 180 degrees is pi over 2. So 270 degrees equal 3 pi over 2. So these are the conversions we can do for now. So we'll also look at how we can convert from radians to degrees. So next we are looking at conversion of angles given in radians to degrees. Example, convert the following angles given in radians to degrees. Now we have pi over 3 radians, 7 pi over 4 radians, 4 pi over 3 radians, and 3.72 radians. We want to convert it to degrees. These are angles. I told us earlier that angles can be measured in radians and or in degrees. Right. Okay, let's start here. Solution. First, we know that 2 pi equal 360 degrees. So, what it means is that 1 radian will equal 360 degrees over 2 pi, and that will give us 180 degrees over pi. So that is 1 radian. 1 radian equal 180 degrees over pi. So it follows that if I want to convert, for instance, 3 pi over 3 radians, so I'll now know that pi over 3 radians equal pi over 3 times 1 radians. And I know that this will be pi over 3 times 180 degrees over pi. And notice that because pi over 3 times 1 radians is the same with pi over 3 radians. So now pi over 3 times 180 degrees over pi, which is for 1 radian. Now this one can cancel this. We have 180 degrees divided by 3. 180 divided by 3 will give you 60 degrees. And that is how, when we converted 60 degrees, what we had was pi over 3. All right. Now we go to the second one. 7 pi over 4 radians is the same as 7 pi over 4 times 1 radians, which is equal 7 pi over 4. Then 1 radian is 180 degrees over pi. This pi can cancel pi. So what we have there is 7 times 180 over 4. So 7 times 180 degrees divided by 4. All right. Let's do that. 7 times 180 give us 1,260 degrees divided by 4. That will give us 315 degrees. So you see, 7 pi over 4 is radians is equivalent to 315 degrees. Right. Number 3. We have 4 pi over 3. 4 pi over 3 radians. We are asked to convert it to degrees. So this will be the same as 4 pi over 3 times 1 radian. And this will give us 4 pi over 3. 1 radian is 180 degrees over pi. To do that, pi can cancel pi. So we have 180 degrees times 4. 180 times 4. It gives us 720 degrees over 3. And that gives us 240 degrees. So 4 pi over 3 radians is equivalent to 240 degrees. All right, number 4, that is IV. We want to convert 3.72 pi radians. 3.72 pi radian. 72 pi radian to degrees. Now, 3.72 pi radians is equivalent to 3.72 pi times 1 radian, and that will give us 3.72 pi. Of course, 1 radian is 180 degrees over pi. So this pi can cancel pi. We have 3.72 times 180 degrees. 3.72 times 180 degrees give us 669.6 degrees. So that is how it is converted. Now we are going to take another subtopic talking about conversion of angles given in degrees, minutes, and second to decimal degrees. Sometimes angles are given in degrees, minutes, and seconds. Such angles can be converted to decimal degrees. Let's look at example of such conversion. Example, convert the angles given below. Number one angle is 154 degrees, 48 minutes, 12 seconds. Number two is 86 degrees, 37 minutes, 41 seconds to the nearest degrees. So this is how we can go. We have 154 degrees, 48 minutes, 12 seconds. To convert it to degrees, we have 154 degrees. No, already this is in degrees. Now this is in minutes. So to convert that, we say plus 48 over 60. Then plus 12 over 60 times 60. And we know that 60 seconds make 1 minute. So we have 60 minutes times 60 seconds. And that gives us 154. Then 48 divided by 60 give us 0.8. Then we know that 60 times 60 is 3,600. So meaning that this will be 12 divided by 3,600. That will give us about 0.0033. If you add all this, you have 154 plus 0.8 plus 0.0033. We will have 154.833, which is approximately 155 degrees to the nearest degrees. All right. We can also convert the second one. The second one is 86 degrees, 37 minutes, 41 seconds. Then that will give us 86 degrees plus 37 over 60 plus 41 over 3,600, that is 60 times 60. We have 86. Then 37 divided by 60 give us 0.612 plus 41 divided by 3,600 give us 0.011. It's very simple to convert. So when you add all these, you have 86 plus 0.612 plus 0.011. This will give us 86.623. Now to the nearest degrees, you can call it 87 degrees. So this is how the conversion is done. We can also convert angle from degrees, that is decimal degrees, to minutes. And that will take us to another subtopic. So we look at another subtopic, conversion of angles in decimal degrees to angles in degrees, minutes, and seconds. For example, convert the following angles given in decimal degrees to degrees, minutes, and seconds. Correct your answer to the nearest seconds. All right? Now, I will take the solution of 1. I have 134.823 degrees. 134.823 degrees. I want to convert it to degrees, minutes, and seconds. So what I will do, this will be equal to 134 plus, now see this one, which is the whole part. We'll first write the whole part. Then the decimal part is 0.823 times 60. Remember, when we were converting from minutes to degrees, the first minute there will now divide it by 60. And we know that division is opposite with multiplication. So now, the decimal part will be multiplied by 60. Of course, if we do that, we have 134 plus 0.823 times 60 will give us 49.38. All right. So we have another decimal part. So we'll then write it in this form, plus 49. Now this is 49 minutes. So we'll now go for the second by saying 0.38 times another 60. Now look at that. Here we still have decimal, because the decimal part is 0.38, which is equivalent to 0.38, so times 60. If we do that, we'll have 134 plus 49 minutes. Then this will give us 0.38 times 60, give 22.8. And we were asked to correct our answer to the nearest second. So this gives 34 degrees, 49 minutes, and then 23 seconds. So that is how the conversion is done. I'd like to take the second 1, we have 76.253 degrees. It will be the same as 76 plus the decimal part is 0.253 times 60. If we do that, 0.253 times 60 give us, we have 76 degrees, and this is a 15.18. Of course, this is 15 minutes. This is the second. So we'll go again by saying 76 degrees 15 minutes times, let me do this first, 0.18 times 60 again. So if you do that, 0.18 times 60 give me 10.8. So we have 76 degrees 15 minutes, then 10.8 seconds. If I take it to the nearest second, I will have 76 degrees 11 seconds. So this is how we convert angles from degrees, minutes, second. We can convert it to degrees, decimal degrees. We can also convert from decimal degrees, like what we have done, to degrees, minutes, and second. All these are measurements of angle. All right, so we'll look at the next subtopic. In this section, we are going to look at quadrants. We will now consider the line where we started before, that we said that if the line OP, we drew a line starting from the point O to another point P. Okay, so suppose the line OP rotates about the points O. The movement of the line back to its starting point from a circumference of a circle. Now, this is what we are saying. This is the point 0. So this line, this particular line, rotates here and come back to this point. It rotates anti-clockwise. Now, if it rotates clockwise, the value of the angle, it will give us negative angle when it rotates clockwise. When it rotates anti-clockwise, it give us positive angle. Now, let's the circle that you are seeing can be divided into 4 by the Cartesian plane. So I'm going to place it on the Cartesian plane. If I do that, I will have something of this nature. This is x axis, and this is the point 0, which we know. This is a y axis. Now, this particular one is called the first quadrant. This is the second quadrant. And this is the third quadrant. This is the fourth quadrant. Look at that. So it has divided it into 4. The circle there. You can divide it into 4, where this is the first, second, third, and the fourth quadrants. Now, let the line OP, I want to place the line OP on the first quadrant. If I do that, I'll have a diagram of this form, where is the x axis. So this is the point, the origin, 0, taking it to any point P, which have coordinate xy, and it makes an angle here, theta. And I have said that when it moves, the line OP was here from point P, so it has moved now to P prime. In the process of the movement, it has swept out angle, which is theta. Now let theta, for instance, be 30 degrees. So if the movement is this way and it forms angle 30, then I can also measure its equivalence when it moves from clockwise direction. For instance, 30 degrees, because we know that if you move complete cycle is 360 degrees. But because it's moving clockwise, I have minus 360 degrees plus 30 degrees. How? Because if I want to find the equivalent angle to 30, but the negative aspect, then I must say minus 360 plus 30, which will give me minus 330. So the position of 30 for theta here is equivalent to minus 30 when it moves, or minus 330 when it moves in the clockwise direction. So now there's another thing again, very important, that here I want to drop this. I also drop this. Let this point be point S. No, this is y-axis. Let this point be point R. Now OR is called the projection of OP prime. The projection of OP prime on OX. All right. Similarly, OS, this side, from here to here, OS is called the projection of OP prime on OY axis, on OY. So it becomes very important for us to know that OR is the projection of OP prime on the OX axis. Same thing happened, OS is the projection of OP prime on OY axis. Now, I'd like us to look at some examples of negative and positive angle, the equivalence of negative and positive angle. I would like to also deal only on the first quadrant. All right. Example, find the negative angles corresponding to the following positive angles. 1, I have 45 degrees, 60 degrees, 72 degrees. All these ones are in first quadrants. So I'll start with 45 degrees. Now, I've said that it will be in the first quadrant first. Now suppose this is 45 degrees. When the line OP prime, which was OP here, it now moved to here in anti-clockwise. So if you move from here to here, anti-clockwise, we move from here to here. It means that this side, see the movement in this side, will be negative because it's moving clockwise. So it will be negative. But when it moves anti-clockwise, it's positive. So what I will do is minus 360 degrees plus 45 degrees. So if I do that, minus 360 degrees, 45, 5, I have 5 here is 1. Okay, so I have minus 315 degrees. So minus 315 degrees. So what it means is that 45 degrees in the positive direction is equivalent to minus 315 degrees in the negative direction, that is the clockwise direction. II is 60 degrees. So minus 360 degrees plus 60 degrees will give me minus 300 degrees. So that means in the first quadrant, here 60 degrees is equivalent to minus 300 degrees. Then we go again, I. That 70 degrees, no, minus 360 degrees plus 72 degrees. To do that, we have minus 72, 8, minus 288 degrees, minus 288. So it means that 72 degrees equivalent to minus 288 degrees. Now 72 degrees is anti-clockwise rotation, while minus 288 degrees is clockwise rotation. Okay. Now the next subtopic we are looking at is basic trigonometric ratio. Right. Consider the right angled triangle below, which is extracted from the first on the first quadrant. Okay, look at what I'm saying. We know that the first quadrant is this, and this is the line that rotates from this x-axis to this place. Let here be from 0 to p. Now, we'll also drop the projection. And we know that this is y-axis. So if this is y-axis, then this is also y-axis. Why this is x-axis. So I want to extract it out, this right angle triangle. I will have something like this. I will have something like this. You know what I want to do here? I want to bring it so that it will be bold. So I have something like this. Points. Let me call it A, B, C. Now, this is the same right angle here. I just bring out the right angle. I only turn it like this to have here so that it will be bold to see. This side is A, facing angle A. And then we call it opposite. Opposite to theta, because this is theta. This side is C. Of course, C is adjacent. Adjacent. It is adjacent to theta. Adjacent means side to theta. Then we also have this side B, which is hypotenuse. Hypotenuse. Okay, so this is the right angle triangle. Now, what do we want to see? We see the ratio that sine theta is opposite all over hypotenuse. Then cos theta is adjacent all over hypotenuse. We also have tan. Tan theta is opposite over adjacent. Now, most times we use something to remind us. I remember something like su, ka, toa. Now, here, where S stands for sine, C is for cosine, the short form of cosine is cos. So, then T is for tan. So that's why sine theta is opposite. O stands for opposite over hypotenuse for H. And cosine is adjacent over hypotenuse. Then tan or tangents, call it tangent of angle, the short form is tan, is opposite over adjacent. Now, other angles are secant theta. Secant theta is 1 over cos. 1 over cos theta, and that will give us 1 over sine here, which is opposite by hypotenuse, is the same thing as, look at A over B. Then this is adjacent. Adjacent is C, and then hypotenuse is B. So we then have that this will be 1 over cos, which is C over B. Of course, this will give us B over C. Another one is cosecants. Cosecants. The short form is cosec. Cosecant theta is 1 over sine. Sine theta, which is 1 over A over B. So this gives us B over A. All right. Then we have another one, cotangent. Cotangent theta is 1 over tan theta, and that is 1 over, tan theta. Tan theta is opposite, which is A over C, adjacent. So we'll have A over C, which is C over A. So these are the angles, the basic trigonometry ratio. So we are going to use it to work further from now on. Now, these basic trigonometry ratios here define the relationship between the angles and the sides of the triangle. Now, there's one important thing to note. This place that is adjacent can also be opposite if theta is here. If theta is here, then this side become opposite and this side become adjacent. So this is opposite because theta is here. Now notice that since theta is here, this side is opposite to theta. So if theta were to be here, then this side will be opposite to theta here. But the hypotenuse remains the longer one. Now the relationship here that we see is between the angles and the sides, and that will take us to a formal definition of trigonometry. This is a branch of mathematics that studies the relation between the angles and sides of a triangle. So trigonometry is a branch of mathematics that studies the relationship between the angles and the sides of a triangle. Okay, I want to go back to the quadrants. Now that we know basic trigonometry ratio, we'll go back to several quadrants that we have already looked at. We will start again in the first quadrant and use this relationship so that we can learn more about that. Now look at this. This is the point, and this is theta. Let me drop the projection here, and this is x, as we know, this is y axis. Right, we now see that in the first quadrant, sine theta, sine theta is opposite all over hypotenuse. Now this is opposite. Let the line OP be represented by R. So we now see that we have sine theta equal y over r. Then cos theta is adjacent over hypotenuse, that is x over r. Then tan theta is opposite over adjacent, y over x, that is tan. Now, the three, sine, cos, and tan, are all positive. They are all positive in the first quadrant. Now, let us move to the second quadrant, because the second quadrant can only define acute angle. What we mean by acute angle, angle between 0 and 90 degrees. So we want to extend the definition to other angles. That will take us to the second quadrant. This is the first quadrant. So the second quadrant. We also consider the second quadrant. Now the line OP has rotated anti-clockwise to the second quadrant. Look at here. And if that happens here, it forms angle theta here. I will also drop the projection. And since this is x-axis, we all know that this is also y-axis, and that here will be y. Y here is minus x. Minus x, because in the Cartesian plane, the left-hand side is negative. The right-hand side is positive. So we now see that in the second quadrant, sine theta, sine is opposite. Now look at it. Opposite over hypotenuse. Opposite over hypotenuse. That gives us y over r. Cos or cosine theta is adjacent, that is minus x over r. Then tan theta is opposite, that is y over minus x. Opposite over adjacent, which is the same as minus y over x. Then we then see that in the second quadrant, only sine is positive. Only sine is positive. So we will then define angle in the second quadrant, which is above 90 degrees. That is above acute angle. What we are talking here about is obtuse angle. Angle that is above 90 degrees, but less than 180 degrees. That is between 90 and 180 degrees. It is only sine that is positive there. So we will have the definition now, how we define angle in that particular quadrant. From what we have done, we can define angle in the second quadrant, that sine 180 minus theta equal y over r, which is equal sine theta. Then cos 180 minus theta will equal minus x over r, which is minus cos theta. And 180 minus theta is equal minus y over x, which is equal minus tan theta. Because from the position that the line OP rotates to the second quadrant in anti-clockwise, we have seen from the diagram that it is only sine that is positive. So cos is negative, and then tan is also negative. And in the second quadrant, you know, we have the maximum of 180 degrees. So for any angle that we need, 180 degrees minus the angle can give us the supplement. We can then see that in the second quadrant, the sine of angle is equal to the positive is numerically equal to the positive of the sine of its supplements. Also, the cosine of angle is numerically equal to the negative of the cosine of its supplements. The supplement of angle is the angle that when added to another angle, it gives you 180 degrees. That's what we call the supplement. Now you now see that in cosine, look at it, cos 180 minus theta will be equal minus cos theta. So that's why we said that the numerical value of cos theta will be the same with the negative of cos theta in the second quadrant. Same apply. The tangent of angle in the second quadrant is numerically equal to the negative of the tangent of its supplement. So it is only sine that is positive in the second quadrant. Now let us take practical example so that we see how we can solve problems that relate to second quadrants. So example, find the numerical values of the following angles: I sine 55 degrees, cos 140 degrees, and tan 95 degrees. Okay, we know that these angles 155, 140, 95, they all fall in the second quadrants. Therefore, by definition, we know that sine 180, I want to get 155. So sine 155 is the same as saying sine 180. Okay, let me do that. Sine 155 degrees is the same as sine 180 minus 25, which is equal sine 25 degrees. So sine 155 is the same as sine 180 minus 25. Of course, 180 minus 25 will give you sine 25. Because by definition, we said that sine 180 minus theta will be equal sine theta. Cos 180 minus theta will be equal minus cos theta. So for cos 140 degrees is the same as cos 180 minus 40 degrees. You see that? And that will be equal minus cos 40 degrees. Now, since we need the numerical value from the first one there, you can press it using your calculator. Press sine 25. It will give us 0.4226. Okay, so cos 40 or minus cos 40, this will give us minus 0.7660. 660. Okay, so the same is true for tan. We need tan 95 degrees is the same as tan 180 minus 95. That gives us 85, which is equal minus tan 85 degrees. Tan 85 degrees. So tan 85, that gives us minus 11.4301. That is tan. So what we are saying is, if you press sine 155, it gives you the same thing sine 25 will give you. And then sine 25 is what we call the supplements of 155. If you also press cos 140 degrees, it gives you the same with minus cos 40 degrees. All right? Then tan 95 degrees give you the same with minus tan 85 degrees. All right, so that is the definition in the second quadrant. And this will now take us to the third quadrant. The third quadrant. Now, we also consider the diagram. Now, the points OP that we were considering, the line OP, has rotated anti-clockwise to the third quadrant. And then, if we drop this projection, in this axis we have minus y axis, this side is minus y. Then we still have minus x, because this is where theta is formed. We can now define it based on the ratio, the trig ratio, that sine theta is, this is r. So sine theta is minus y over r. Then cos theta, cos is adjacent that is minus x over r, tan theta. Tan is opposites over adjacent, that is minus y over minus x, which is y over x. Now, in these quadrants, we see that tan is positive. Tan is positive in these quadrants. We can then define, give the definition of the third quadrant in this way. That in the third quadrant, sine 180 plus theta. Look at that, sine 180 plus theta is equal minus y over r, which is equal minus sine theta. Cos 180 plus theta is equal minus x over r, and that is equal minus cos theta. Tan 180 plus theta will be equal y over x, and that is equal tan theta. So in the third quadrant, we have that the tangent of angle is positive. The tangent of angle is positive. Now, based on this definition, we can have some examples and see how we solve problems in the third quadrant. Now, let's look at this example. Find the numerical values of the following angles. I will start with I, sine 230. And we know that sine 230 degrees is more than the second quadrant, which is 180. Now, how do we get 230? We know that sine 230 degrees will be the same as sine 180 degrees plus 50 degrees. Look at that. Sine 180 degrees plus, and that will give us minus sine 50 degrees. According to definition, see what we said here. Sine 180 plus theta will be equal minus sine theta. So here, 180 plus 50, theta is 50. So it will be equal to minus sine 50. And if we check the numerical values, it will be the same with this. That is what we are saying. So from our calculator, we can see sine 50 degrees. So it will give us minus 0.7660. Because sine 50 degrees is 0.7660. But because of the negative, so it will be minus. And if you press sine 230 degrees, see, it will give you negative. All right, so we now go to cos 210 degrees, 210 degrees. By definition, it will be cos 180 degrees plus 30 degrees. Yes, because 180 plus 30. So that will be equal minus cos 30. The numerical value then become minus 0.866660. Then tan, another one is tan 212 degrees, that is 212 degrees. And we know that 212 degrees, then this is you have 2, 3, 1, 180 plus what will give you. So we can just see 210 degrees minus 180 degrees. So 32 degrees, because this is 11, this is 3, 1. Okay, so if you add 32 degrees, you have that. So tan 2120 is the same as tan 180 degrees plus 32 degrees. So that is equal tan 32 degrees. In that place, tan is positive, so tan 32 degrees. And the numerical value become tan 32 degrees is giving us 0.6249. All right, so that is how we solve problem based on this angle. Let's look at the last quadrant, that is the fourth quadrant. And then after the definition, we also take practical example. We are looking at the fourth quadrant. Now, we consider the diagram. Suppose the line OP rotates up to the fourth quadrant, so that we have the point here on xy, and then this is theta. Then I drop the projection, where here is minus y. This is x, because it's in the positive direction of x-axis now. Because this is the y-axis, and this is, this is positive y, this is negative y. This is r. So we see that sine theta is opposite. This is minus y, opposite, over hypotenuse, which is r. And then cos theta is adjacent over hypotenuse, that is x, over r. Then tan theta is opposite, that is minus y over adjacent, which is x. And we have that. We can then define angles in the fourth quadrant in this way, that sine 360 minus theta will be equal minus y over r, which is minus sine theta. Now notice that sine is negative. So that's why we have sine 360 minus, because the whole rotation is 360. So if you say 360 minus theta, it will give you this angle. It will give you the position of the line. All right? So cos 360 minus theta degrees will be equal x over r, which is equal cos theta. Now notice that in the fourth angle, cos is positive. Then we also have that tan 360 minus theta equal minus y over x, which is minus tan theta. So in the fourth quadrant, only cos is positive. We can summarize this using this initial, that here all the angles are positive from what we have seen. From the first quadrant, all the angle is positive. Then if you come here, sine is positive, that is in the second quadrant. Then in the third quadrant, tan is positive. In the fourth quadrant, cos is positive. So we have this as a reminder. As a reminder, if you read from C to this side, it's like cast. So cos is positive in the fourth quadrant. The first quadrant, all the angles are positive. In the second, it's only sine. Then in the third, it is tan. That is positive. All right, so in the fourth quadrant you are dealing with, we'll take some practical examples and see how we can solve problems related to the fourth quadrant. Example, find the numerical value of the following angles. We have sine 310 degrees, cos 342 degrees, and tan 280 degrees. So we take the solution. By definition of the fourth quadrant, we know that sine 360 minus theta will be equal minus sine theta, and then cos 360 minus theta degrees will be cos theta. Tan 360 minus theta degree will be minus tan theta. So what we'll do now is to look at sine 310 degrees. Now sine 310 degrees is the same as sine 360 minus 50 degrees. So that is the same as minus sine 50 degrees, because 310, when you say 360 minus 50, it gives you back 310. We do same to cos. Cos 342 will be cos 360. Now 360 minus 342. We have 360, 342, 8, 1. So that's 18. 18. So minus 18 will be minus cos 18 degrees, because 342 plus 18 will give you back 360. Tan, okay, sorry, cos, not minus, but cos 18 degrees, because at that quadrant, cos is positive. You look for tan, 280 degrees, give us tan 360 minus, now if you say 360, then you have 280. This 16, you have 80 minus 80, yes, degrees. That gives you minus tan 80 degrees. All right, minus tan 80 degrees. Okay, so we can then use calculator to have the values of minus sine 50, cos 18, and then minus tan 80. This is how angle in the fourth quadrant are solved. All right, we want to look at angles above 360. What about if we are given angles that are above 360? How do we get their values? Okay, angles, that takes us to the next topic, angles greater than 360 degrees. Given any angle greater than 360 degrees. we recall that one revolution is 360 degrees. Thus, minusing 360 degrees from the given angle, the given angle, the remaining angle falls into any of the quadrants depending on the given angle. Now, let me explain what I'm trying to say here. If we are given angle that is greater than greater than 360 degrees, for instance, I want to look at angle 480 degrees. And I know that 480 degrees is more than 360 degrees, which is one revolution. So what I would do is to minus 360 degrees from the 480 degrees. And look at this, 480 degrees minus 360 degrees. This gives me 120 degrees. This 120 degrees is called basic angle. Basic angle. Now this 120 degrees must fall in the second quadrant again. And then I will now start the definition based on the second quadrant. Okay, so if it was maybe 500 degrees, so what I will do, I will rotate the first time. The remaining one, wherever it falls, I'll then start the definition. It can be up to 800 degrees. It doesn't matter. I'll just rotate the first one. I'll rotate the second one. Of course, I know that if I rotate the first one, it's 360. The second revolution is what? Then that will give me 720, so it remains 80 degrees. So you see that angle of this nature, 880 degrees, is equivalent to 80. Because if I remove 720 degrees, it remains 80 degrees. And this 80 degrees falls in the first quadrant. So I will now also define it based on that. That is what I'm trying to say here, that given any angle greater than 360, we record that one revolution is 360. Now thus, minusing 360 from the given angle, the remaining angle falls into any of the quadrants depending on the given angle. The remaining angle is called the basic angle. So I have to put that. The basic is the basic angle. So we are going to take the practical example of this. So we look at an example. Find the basic angle of the following and hence indicate the quadrants in which they lie. So let's take the solution of the first one, I. 390 degrees. You see, 390 degrees is more than 360 degrees. So what we'll do is, we know that 360 degrees, that is one revolution. One revolution. 360 degrees is one revolution. And then we know that one revolution plus 30 degrees. Look at that. One revolution is 360 plus 30 degrees. So 30 degrees is called the basic angle. It's called we were asked to find the basic angle. So 30 degrees is the basic angle. And which quadrants does 30 degrees fall? That is the first quadrant. So it implies that 390 degrees is in the first quadrant. That's what it means. Since the basic angle falls in the first quadrant, it means that 390 is also in the first quadrant. Okay, the second one. We are given 600 degrees. Of course, 600 degrees, if you bring out 360 degrees, that is one revolution plus it gives us 240 degrees plus 240 degrees, because 360 plus 240 degrees will give you 600. So here 240 degrees is the basic angle. And where does 240 degrees fall? 240 degrees is in the third quadrant, because 180 is in the second, then 240 is in the third. And that implies that 600 degrees is in the third. In the third quadrant, because the basic angle is in the third quadrant. 744 degrees. 744 will be equal. Now, it will be equal 720 is 2 revolution. 720 is 2 plus 24 degrees. 720 plus 24 will give us 744. So now 24 degrees falls in the first quadrant, is in the first quadrant. Therefore, 744 degrees is in the first quadrant. So that is how it is measured. If it is even more than this, you just look at the revolution and count it out. Then the remaining one is called basic angle. Whichever quadrant that one falls is where the main angle, the given angle, also falls. All right. So we are going to move to another topic, and then that is about the Pythagoras theorem. So we are going to look at the Pythagoras theorem. Now consider the right angled triangle below. Have a right angle triangle. Is A, B, C, and I have side A here, B, and C. The Pythagoras theorem states that the squares of the two shorter sides. Now the two shorter sides are this way. Let's say the adjacent and opposite. Square of the two shorter sides, that is opposite and adjacent, is are equal. It says that the sum, state that the sum of the squares, the sum of the squares of the two shorter sides, that is what the Pythagorean theorem states. The sum of the squares of the two shorter sides are equal to the square of the longer side, that is hypotenuse. So mathematically, you can write this as AB square plus BC square will be equal AC square. Okay. So look at that. AB square plus BC square is equal AC square. That is the length. Talking about the length. No, when we put this absolute value sign, I'm directing it to the length. And the length of the adjacent sides, the square of the length of the adjacent side, plus the square, the length of the opposite side, is equal to the square of the hypotenuse. All right, that is the Pythagorean theorem. We can prove this. Proof. And this is D. Okay, consider the triangle above with 90 degrees at A. That is, it has right angle at A. That's why I put that. Now, from triangle A, B, C, this triangle A, B, C, cos B, look at that. Now, if this is B, this side is B. If this is C, this is C, because the whole of this is A. Now from the whole triangle ABC, cos B is equal, when I say cos B, I'm considering this angle now, is equal adjacent over hypotenuse. And here, adjacent is this side, that is C over A. And then, if that is the case, we can also consider also from triangle A, BD, that is, I'm looking about from here to here, this triangle. I also see that cos B is equal P because at that point, if you look at this, at that point, this becomes hypotenuse and not this again. So it's the same as P over C. So that implies that cos B equal C over A, which is equal P over C. Now let us cross multiply C over A and P over C. By cross multiplication, you have that C square equal AP. That is 1. We can also consider triangle ABC. That is this, goal of this, the whole triangle now. If you consider that, then cos C, that is here, cos C is adjacent, which is B. When we talk about this side now, this side become opposite. When you talk about this angle, this side become, which is B over A. So this is the hypotenuse represented by A. Also, from triangle ACD, that is this particular triangle, cos C will be what? Cos C will be, and this is hypotenuse to that one, if we check. So it will be Q over B. Q over B. So now I can then say that B over A equal Q over B. That is for cos C, comparing the two. By cross multiplication, I see that B square equal AQ. That is equation 2. Now, adding 1 and 2, adding equations 1 and 2. See equation 1 here, and this is 2. We'll have that C square plus B square will be equal AP plus AQ, right? So, which we can write C square plus B square equal AP plus Q. We can factor out A and get P plus Q. And what is P plus Q? From here, P plus Q give you the whole of A. So we can then write it like this, that C square plus B square equal A times A, and that is A square. So C square plus B square equal A square. And then that proves the Pythagoras theorem, which says that the square of the two shorter side will be equal to the square of the sum of the two shorter side will be equal to the square of the longer side. Now see, C here is one of the shorter side, B is one of the shorter side. Now this is the longest side here. So that proves the Pythagoras theorem. So we'll now take an example and see how we can apply the Pythagoras theorem to solve trigonometric problems. For example, in a right angle triangle XYZ, XY is 12 centimeters, XZ 15 centimeters, and then find YZ. So we'll draw the right angle triangle. This is X, Y, and Z. It has right angle here. So xy is 12 cm. Xz, okay, is 15 cm. Now they ask us to find yz. So by Pythagoras theorem, you know that xy plus yz square will be equal xz square. All right, so that means xy, which is 12 square plus yz square will be equal 15 square. And we know that 12 square is 144. And then 15 square is 225. 225. 12 square is 144. So we need yz square, which is 225 minus 144. 225 minus 144. All right. That gives 81. So yz square equal 81, meaning that yz will be square root of 81, which is 9, because 9 cm. So you see that by Pythagoras theorem we are able to find the side of the unknown side, that is yz. All right, this will take us to another subtopic. Now, the next subtopic we are looking at is complementary angle. Consider a right angle triangle below. Right angle triangle below. Angle A, B, C. Now, we know that this right angle triangle has the total angle of 180. So with 90 degrees at B, it means that this is alpha and this is angle beta. So it means that 90 degrees plus alpha plus beta is 180 degrees, the total angle. Now, since there is 90 here, alpha and beta are called complementary angle because they are also 90 degrees. That is alpha plus beta equal 90 degrees. That implies that alpha will be equal 90 degrees minus beta. Then beta will also be equal 90 degrees minus alpha. Then it follows that sine alpha will be equal cos beta, which is equal cos beta minus alpha. You see, that is sine alpha will now be cos 90 degrees minus beta. So cos alpha will be equal sine beta, which is equal sine 90 degrees minus alpha. Okay, sorry, minus alpha. This is 90 degrees minus alpha. So, for instance, sine 45 degrees will be equal cos 45 degrees. So if you see sine 35 degrees, for instance, it will be equal to cos 55 degrees. The reason being that if you add the two, you have 90 degrees. So that is what we call a complementary angle. All right, that takes us to basic trigonometry ratio of special angle. Basic trigonometry ratio of special angles. We start with 0 degrees and 90 degrees. So you consider the right angle triangle below. Look at this. We have here 1, y, and this is x. Now, he has angle theta. Look at this right angle triangle. Theta is here. If theta decreases and y decreases, if theta decreases to 0 and y decreases to 0, that is, if theta decreases to 0, y decreases to 0, then x approaches 1. You know, by the time y becomes 0, theta goes to 0. Then you see this hypotenuse will fall to 1. In the x-axis, it will become 1. Then we can then see that in such approach, if I need sine 0, so look at this, sine 0 degrees, and we know that sine is always opposite over hypotenuse. Sine 0 equal y over 1, and y is 0, so you have 0 over 1, which is 0. So if I go for cos 0 degrees is adjacent over hypotenuse, that is x over 1. That gives me 1 over 1, which is 1. Notice that. So now tan 0 degrees, tan is opposite over adjacent, y over x, which is 0 over 1, and that is 0. So we have that cos 0 is 1, sin 0 is 0, and then tan 0 is 0. All right, so we can also define same for 90 degrees. So we can also define in terms of 90 degrees. For instance, sine 0 degrees equal cos 90 degrees, which is equal 0. Then cos 0 degrees equal sine 90 degrees, which is equal 1. Tan 0 degrees, tan 0 degrees equal 0, because here we see that tan 0 is 0. You have seen that it is y over x. And then that is equal to 0 over 1, like we have said, which is 0. Now what about tan 90? Tan 90 degrees now become y over 0. And we know that you cannot divide any number by 0. So that gives you undefined. Undefined. Or at times we write it in this way, which means undefined. Now, with this, we can be able to see that with the idea of complementary angle, you can find 0 degrees and the 90 degrees. Now, the next one will be, we'll look at 30 degrees and 60 degrees is the next one. And we are going to consider the triangle below. We have this triangle, and this triangle, triangle ABC. It has its equilateral triangle. So it has 60 degrees here. It has 60 degrees. We also have 60 degrees. Now, dividing or bisecting, let me use that word, bisecting, triangle ABC. You know, when I say bisect means dividing it into equal parts. Meaning I can divide this way, it will still be the same. I can divide any way I want to divide. But if I bisect, I will have another triangle of this form. So here gives me 30 degrees. 30 degrees is A, and this is B. This remains 60 degrees, and this is 60 degrees. Let this point be D. So I have 2, 2, and this is 1. Now, I'm going to consider one of the triangles because the two triangles are equal. Now, considering triangle ACD, that is this part, I have something like this, where here is 30 degrees, and this is D, on D, give me 90 degrees, and this is C with 60 degrees. So, by Pythagoras theorem, this is 1. So, by Pythagoras theorem, I know that AD square plus DC square equal AC square. So that means AD square plus 1 square equal 2 square, which means AD square is 4 minus 1, because 2 square is 1 is 4. Then you transfer this, have this, which is 3. That is AD square. So that AD will now be the square root of 3. So if we have that, we can then see that this triangle here has root 3 here. Now, I want to consider 30 degrees. 30 degrees in terms of sine, cosine, and tangents. There, we will see that sine 30 degrees is opposite over hypotenuse, that is 1 over 2. Cos 30 degrees, look at this, 30 degrees. So cos is this way. Adjacent over hypotenuse, root 3 over 2. Now tan 30 degrees is opposite over adjacent. Opposite over adjacent. Give me 1 over root 3. All right. So for 30 degrees, we have finished that with the ratio. We now go to 60. So sine 60 degrees, sine is sine 60. Now 60 degrees. So opposite is this way. Sine 60 degrees is root 3 over 2. Cos 60 degrees is this way, is 1 over 2. That is cos adjacent over hypotenuse. Now what about tan? Tan 60 degrees equal, tan is opposite all over adjacent, which is root 3. That is root 3 over 1, which is root 3. All right. So we then see we have done it for 0, 90 degrees, 30 degrees, and 60 degrees. We can also extend it to other angles so that we can then put them all together in a table. So the next is 45 degrees. Let's look at angle there in 45 degrees. For that, we consider the unit square. Given below. Unit square means it has 1, 1. The sides is 1, 1. And we know that this is 90 degrees. Here is 90 degrees. Here is also 90 degrees. A, B, C, D. Now, if I diagonalize the square, I will have it in this form. This will divide this. You can also diagonalize it this way. Then I will have a triangle of this form. Look at that. Where this is 45 degrees, because here is 90, so as you divide it, it's 45 degrees. Here is also 45 degrees. Here is still 90. Now this is A, B, C. Here is 1. This is 1. So here, by Pythagoras theorem, I have that AB square plus BC square will be equal to AC square. This side square plus this side square will be equal to this. And this is 1 square plus 1 square equal AC square. This is 2 equal AC square. That means AC is equal root 2. So this side is root 2. Now, if that side is root 2, then sine 45 degrees, that is, I'm looking at 45 degrees from here. If you look from here, it's still the same because the two are the same. So it is now opposite over hypotenuse. This is 1 over root 2. Cos 45 degrees is the same, 1 over root 2. Cos is adjacent. And so if we are looking from here, it's adjacent over hypotenuse. Tan 45 degrees is equal opposite over adjacent. Opposite over adjacent is 1 over 1, which is 1. So we have now defined it from 0, 90 degrees, 30 degrees, 60, and 45. Let us look at another one, like 180 degrees and 270 degrees. Let's look at the values too, because we want to get a table and put those values. We know that, let's look at 180 first. By definition, in the second quadrant, sine 180 minus 0 will be equal sine 0 degrees. Of course, we know that sine 180 minus 0 is equal to sine 180, because 180 minus 0 is 180, which is equal 0 degrees. Okay, is equal, which is sine 0. And what is sine 0? Sine 0 equals 0. Now, cos 180 degrees. Yes, let me take that. Cos 180 degrees, let me start here, is equal cos 180 minus 0 degrees, which is equal minus cos 0. Now look at that, minus cos 0. And what is cos 0? 1. So give you minus 1, which is minus 1. So cos 180 will give us minus 1. Tan 180 degrees is equal tan 180 minus 0 degrees, which is equal minus tan 0, minus tan 0 degrees. And we know that this will give us minus 0, which is 0. So tan 180 is also 0. That is for 180. We can also define it for 270. So if you go 270, sine 270 degrees is the same as sine 360 minus, now if we say 270, yes, 360 minus 90 degrees, which is equal sine 90 degrees. And we know that sine 90 degrees is 1. Okay, that is in the third quadrant. So this is minus. So this gives us, this is equal minus 1, which is minus 1. Because minus sine 90 degrees and sine 90 degrees is 1. So we have minus times 1, which is minus 1. That is sine 270. Again, cos 270 degrees equal cos 360 degrees minus 90 degrees. Of course, in the third quadrant is only tan that is positive from what we have seen. So this will give us minus cos 90 degrees. This is equal, cos 90 degrees is 0. So that is 0. Now tan 270 degrees equal tan 360 minus 90 degrees. And that gives me tan 90 degrees. At that point, tan 90 degrees is not defined. So it's undefined. All right, so we will collect all these results and put it on a table. That is what we'll do now, collect all the results and put it on the table. All right, so we have the table in this form for 0 degrees, 30 degrees, 45, 60, 90, 180, and 270. Then for 0 degrees, sine 0, look at there, sine 0 is 0, cos 0 is 1, tan 0 is 0. Then let's read 90 degrees at that point, because we're using 0 and 90 first. So sine 90 degrees is 1. You can see sine 90 degrees being equal to cos 0. Then cos 90 degrees is 0. Tan 90 degrees is undefined. It's It's not defined at that point. So 30 degrees, sine 30 degrees, sine 30 degrees. We see sine 30 degrees is 1 over 2. So 30 degrees, 1 over 2. Cos is root 3 over 2. That is cos 30 degrees. Root 3 over 2. Then sine 30 degrees is 1 over root 3. For 45 degrees, we see that 45 degrees, for 45 degrees, sine 45 is 1 over root 2. Look at it here. Cos 45 is 1 over root 2. Tan 45 is 1. Then 60 degrees, for 60 degrees, we have done something about 60 degrees here. We see that sine 60 degrees is root 3 over 2, root 3 over 2. Cos 60 degrees is 1 over 2. Then tan 60 degrees is root 3, 180. At 180, sine 180 is 0, cos 180 is minus 1, tan 180 is 0, then 270. Sine 270 is minus 1, cos 270 is 0, and then tan 270 is not defined. So we can prepare the table in this way, which gives the value in the range from 0 to 270 degrees. Right. We look at practical examples. Find the values of the following without using calculator. Now the degrees are sine 120 cos 210 tan 330 degrees. Then IV says 1 plus cos 240 degrees divided by 1 minus cos 240 degrees. So we start with 1, that is I. Sine 120 degrees is in the second quadrant. So it is the same as sine 180 degrees minus 60 degrees, which is equal sine 60 degrees. And we know that sine 60 degrees is root 3 over 2. II cos 210 degrees is the same as cos 180 degrees plus 30 degrees, which is equal, this one is in the third quadrant. So it gives minus cos 30 degrees, which is minus cos 30 degrees is root 3 over 2. Then tan 330 degrees, that is III, equal tan 360 minus 30 degrees, which is equal minus tan 30 degrees. Of course, tan 30 degrees is 1 over root 3. So we go IV. 1 plus cos 240 degrees over 1 minus cos 240 degrees. But we know that cos 240 degrees equal cos 180 degrees plus 60 degrees. And that will give us, that is in the third quadrant, so that gives us minus cos 60 degrees. because 240 falls in the third quadrant. And so that will give minus cos 60 degrees. Minus cos 60 degrees. So that gives us 1 over 2. Because cos 60 degrees is 1 over 2. So this gives us minus 1 over 2. And that then this implies 1 plus minus 1 over 2 over 1, then minus 1 over 2. We give 1 plus 1 over 2 over, yes, 1 minus, sorry, this will be 1 minus 1 over 2. Then this is 1 plus 1 over 2. Taking LCM of the upside, we have 2 minus 1 over 2 over 2 plus 1 over 2, which gives us 1 over 2 over 3 over 2. This is 1 over 2. 1 over 2 times 2 over 3, which is 1 over 3. So that's the value. So we look at this example. If tan theta plus tan 30 degrees over 1 minus tan theta tan 30 degrees equal minus 1, find the value of tan theta in short form. So because of our idea of basic trigonometric ratio in short form, we can solve this easily. Now, tan theta plus tan 30 degrees over 1 minus tan theta tan 30 degrees equal minus 1. That is what is given. Then this will imply that tan theta plus 1 over root 3, because tan 30 is 1 over root 3, over 1 minus tan theta, then have 1 over root 3. Okay, so it's equal minus 1. Then if you take LCM of this numerator, we have root 3 tan theta plus 1 over root 3. If you go the downside, we have root 3 minus tan theta over root 3 equal minus 1. That means we can write this as root 3 tan theta, see that, plus 1 over root 3 times, you know, here we will invert it, root 3 over root 3 minus tan theta equal minus 1. Now this can cancel this. We then have root 3 tan theta plus 1 over root 3 minus tan theta equal minus 1. So by cross multiplication, we have that root 3 tan theta plus 1. If you multiply this by here, we have minus root 3 plus tan theta. That is by cross multiplication. If you cross multiply here, minus 1 will multiply it to have minus root 3 plus tan theta. All right, so for me to find theta, I know that root 3 tan theta minus tan theta will be equal minus root 3 minus 1. So I'm transferring minus 1 this way, so that tan theta will be equal root 3 minus 1. See, if you factor out tan theta, you have this, which is equal minus root 3 minus 1. Then tan theta will be equal minus root 3 minus 1 over root 3 minus 1. Or if I don't want to write that, if I don't want to write it that way, I can write it like this: minus root 3 plus 1 over, over minus 1 plus root 3. 1 minus root 3. Because here, minus multiply 1, you have minus 1. Multiply this, you have. So that means tan theta is root 3 plus 1 over 1 minus root 3. That is the value of tan theta. And so if I need theta itself, it will be the tan inverse of this. So it's very simple to solve. So in this particular topic, we are looking at graph of trigonometric functions. We start with graph of y equals sine theta from minus 360 degrees to 360 degrees. Now this is the graph, and this is the theta axis. This is the y axis. From what we have known, we see that at 360 degrees, the value of theta is 0. That is, it cuts the theta axis at 0. This place corresponds to 0. Now look at minus 270 degrees. The curve go to 1. So meaning that at minus 270 degrees, you have the value 1 for sine. Minus 180, 0. Now minus 90 give you minus 1. Okay, so sine 0 is also 0. See, you cut it at 0. At 90 degrees, we have 1. And then at 180 is 0. At 270 degrees, you have it here, minus 1, which corresponds to those tables that we fill. So we see that the highest value of theta is 1 and minus 1. It's very important to note that. Then this particular graph is for y equal cos theta, from minus 360 degrees to plus 360 degrees. We see the same thing, that at minus 360 degrees, 1. Then at minus 270, it cuts at 0. Minus 180 gives you minus 1. At 90, minus 90, 0. Then at 0, look at cos 0 is 1, which we also got from the table. Cos 90 degrees is 0. So it cuts at 0. Cos 180 is minus 1. Then cos 270 is 0. And then cos 360 also go to 1. Now, this is the graph of tan. Graph of tan theta. We're taking the interval at 60 degrees. So we also have this particular graph. So we are going to look at trigonometric identities as the next subtopic. So in this subtopic, we are going to look at trigonometric identities. In mathematics, the word identities or identity means an equation that is true for the variables for the variables involved. So in mathematics, when we say identity, what we mean is it's an equation that the variables that are involved, the right hand side, are also equal to the left hand side. Thus, in trigonometry, trigonometric identities is referred to trigonometric equation that are true for the variables involved. Now, let's consider, to derive this identity, we'll consider the right angled triangle below consider the right angle triangle below. Now, sine theta equal opposite over hypotenuse. Of course, that is A over B. We also know that cos theta is adjacent over hypotenuse, which is equal C over B from what we have learned. And so tan theta is opposite over adjacent. That is A over C. So it follows that secant theta will be 1 over cos theta, which is 1 over C over B, which is B over C. All right, so cosecant theta is 1 over sine theta, which is 1 over A over B, and this is B over A. Now we have cotangents. Tangents theta is 1 over tan theta, which is 1 over A over C, which is C over A, right? Then, by Pythagoras theorem, we see that C square plus A square will be equal B square. Got that? Now, this is Pythagoras theorem. So I use Tariq to denote this because we'll be making reference to this. Okay, dividing through by B square, dividing this through by B square, we have C square over B square plus A square over B square equal B square over B square. And then this could be written as, which is that C over B square plus A over B square equal 1. Now what is C over B? We see that C over B is cos. So cos square theta, A over B is sine. Sine square theta equal 1. This is identity 1. This is what we call identity. So for whatever values of theta, cos square theta plus sin square theta will be 1. Right. Now, dividing star equation star by a square, we will have c square over a square plus a square over a square equal b square over a square, which we can write c over a square plus 1 equal b over a square. And then what is c over a? C over a, look at it here, cot. So cot square theta or cotangent square theta plus 1 equal b over a. B over a is cosec square theta. So this is another identity, I. That is another identity. Now we have two identities here. We can also see that if we divide steric, this equation, by c square, we'll have c square over c square plus a square over c square, b square over c square, which we can write 1 plus a over c square equal b over c square. Now, what is a over c? A over c, from what we have here, is tan. So we can see tan square theta equal b over c. And b over c is secant, so sec square theta. This is another identity. So we have derived 3 identities, this, and this. Now we may want to express sine in terms of cos, or cos in terms of sine. That is, from here now, I know that cos square theta plus sine square theta equal 1. So sine square theta will be 1 minus cos square theta. 1 minus cos square theta, which means sine theta is square root of 1 minus cos square theta. Right? Okay. Then the same thing happens. If I want to express cos too, I can also do that. Cos theta equal 1 minus sine square theta, which means cos theta is square root of 1 minus sine square theta. All right. We can also show that tan theta equal sine theta over cos theta. How? Because sine theta itself, from what we did here, sine is a over b, and then cos is c over b. So let us put that. Cos, we can write it like this: a over b over c over b. Of course, we can write this as a over b times b over c. This can cancel this. So we now get back what? A over c, which is tan theta. We also see that tan theta is a over c. So we can write that tan theta is sine theta over cos theta. This is also identity. So this is identity 3, this is identity 4, this is identity 5, this is another identity. All right, these are all identity. Though identity helps us to solve trigonometric equation. For instance, we'll take application problem. We'll take no. So we look at this example, solve the equations for theta between 0 and 360 degrees. 6 sine square theta minus 5 cos theta minus 2 equals 0. Now, number 2 is cos square theta plus 2 cos theta equal 1. Let me start with 1. That's 6 sine 2 theta minus 5 cos theta minus 2 equals 0. All right. So I know that sine square theta plus cos square theta equal 1. So meaning that sine square theta will be equal 1 minus cos square theta. Now I'm going to replace that in the place of sine. So we'll have 6 1 minus cos square theta minus 5 cos theta minus 2 equals 0. So you see what identity can help me do. So I've replaced that here so that I will have the whole thing in cos. And this will give me 6 minus 6 cos square theta minus 5 cos theta minus 2 equals 0. Now 6 minus 2 is 4. So I can write this equation as minus 6 cos square theta minus 5 cos theta plus 4 equals 0. Look at that. Then I have to multiply it through. I have to multiply it through by minus 1. So that I will have it in this way: 6 cos square theta plus 5 cos theta minus 4 equals 0. Then let x equal cos theta. So we'll have 6x squared plus 5x minus 4 equals 0, which is quadratic equation, which is quadratic. So, and this type, I'm looking for two numbers I will add. This is quadratic equation when it is not in unity. Two numbers I will add to give me 5, and the same two numbers when multiplied will give me the product of 6 and minus 4, which is minus 24. So if you add, you have minus 5. If you multiply, you have minus 24. So the numbers are 8 and minus 3. So we say 6x squared plus 8x minus 3x minus 4 equals 0. Now 8 minus 3 is 5. 8 times 3 is minus 24. So we have 6x squared plus 8x minus 3x minus 4 equals 0. Here, what is common here is 3. 3 is common, 3x. So 3x, then I will have 2x. Sorry, 2x is common. Then here will give me 3x plus 4 minus, of course, 1. Here will be 3x plus 4. Because this time, this give me back minus 3x. This time, this minus 4 equals 0. Which means 3x plus 4 and 2x minus 1 equals 0. All right, so 3x plus 4 equals 0, or 2x minus 1 equals 0, which we can see that x equal minus 4 over 3, or x equal 1 over 2. Now among these, I'm going to let you know that x equal cos. Look at x equal cos theta. So meaning that cos theta equal minus 4 over 3, or cos theta equal 1 over 2. Now this is not defined. This one is not defined. The other one is defined. Of course, you see, if you see minus, okay, take away minus, 4 divided by 3 is more than 1. So it may not be defined. Here is defined. So we take that. Cos theta equal 1 over 2 implies that theta equal cos inverse of 1 over 2. That is cos inverse of 0.5. Now, what will be theta? This is 0.5. That is 1 over 2. And that will be 60. That means theta equal cos 60 degrees. Because cos 60 degrees is 1 over 2. So we now have it in that way. Okay. So with that identity, it is very helpful to solve the equation. Now, I like you to take the second one, and here, because it has already been expressed in terms of cost, so you just go direct to substitute whichever variable you want to substitute and solve. That is how that one. The second one is simpler. Nothing is there. So this is what trigonometric identity can help us do. Now we want to look at another subtopic under a special package, and that talks about compound angle.